All right, let's have a look at our quadrilateral family, if you like, our flow chart of quadrilaterals. Often some of the features for some of the shapes we mistake for other shapes. It's a hierarchy. So the lower down in the hierarchy you go, then the more features you can say. You can always use the features from the shapes above. So for example, if we know the rhombus has some of its own properties, but it would also have the properties of the kite and the parallelogram and the trapezium and theoretically the quadrilateral as well. Not that the quadrilateral has many features, but not the features of a square or the rectangle, because that doesn't flow from the rhombus. So okay, quadrilateral is our most basic shape then. I say it doesn't really have a lot of features other than, it's got 4 sides, not really that useful. Also has 4 angles, terrific. That's pretty much it really. Okay, so then we start branching down. And over here we've got the kite. And what do we know about the kite? The kite is where we define it to be we have pairs of adjacent sides being equal. So the adjacent sides are equal. The other thing we know, as a consequence of that, we end up with the diagonals in the kite being perpendicular. And the other thing we know, and this is one of the ones that is often mistaken, it's the formula for the area of a kite. Most people quote it as the formula for the area of a rhombus, but it's actually the formula for the area of a kite, half the product of the diagonals. But the reason we use it for a rhombus is because the rhombus branches from the kite, so we can use the features of a kite. Over on the other side, we have the trapezium, where it has a pair of parallel sides, just one pair though. And we have an area formula for trapezium, of course, half perpendicular height and the sum of the parallel sides, so A plus B. Okay, now trapezium then branches down to parallelogram. So it has the features of trapezium. Theoretically, if you wanted to use the formula for the trapezium area to find the area of a parallelogram, you could. It now has 2 pairs of parallel sides. Opposite sides in the parallelogram are equal. Opposite angles are also equal. Again, you could prove those things via congruent triangles. The diagonals now bisect each other. So over in the parallelogram, they bisect. And we have an area formula for parallelogram, just base times perpendicular height. Just a note there, if you wanted to prove something is a parallelogram, okay, you could prove any of those features. But also, if you just pick one pair of sides, but prove they're both parallel and equal, then that also is good enough to show it's a parallelogram or prove it's a parallelogram. Well, coming from the kite and the parallelogram, over there, well, first of all, there's the rectangle, which is just from the parallelogram. Now, one of the angles is 90 degrees. But then using our different parallel line theorems, we could easily prove all the angles, therefore, must be 90 degrees. And the diagonals now become equal. And, well, area of a rectangle, as we know, length times breadth, or however you want to say it. The rhombus is both a kite and a parallelogram. So in a kite, for instance, the diagonals were perpendicular. In a parallelogram, the diagonals bisected each other. So in a rhombus, they do both. They bisect at right angles. The other feature of a rhombus is that they bisect the vertex. So the angle would bisect the vertex. And then we have the square, which I guess is what we could call the perfect quadrilateral. It doesn't really have any of its own features. It's just that it has all the features of all the quadrilaterals. And if you wanted to give it a feature, I guess you could say, well, the area is the side squared. Oh, well, there's a feature of a square. There we go.